Another information is I found something very interesting in YouTube, and I would like interested student to go and visit. The name of that video is Antiquity of Indian Astronomy. Okay, it's a very interesting video, and something you will find someone telling about Newton, Lagrange, and how Indian astronomy was fantastic at a particular time. So just go and visit, and let us now continue our story of physics. So what are we planning to do? So our plan is to write the Lagrangian of a non-relativistic particle. Now how to do that? Okay, let's take a quick look. Okay, so consider you have E field. Okay, and let us work in 3 dimension. So the E field that is present in the space is a function of r and t. Okay, we all know what is r. And similarly, the magnetic field that is present in the space is also a function of r and t. Okay, and I hope all of you remember how to write the Lorentz force equation. So force on that particle is equal to charge of the particle. So this is electric field here, and then this is the velocity of the particle cross magnetic field present divided by c. In most of the book you will find this c, and in many books they say they take c is equals to 1. Anyway, so why am I writing this force equation when I need the Lagrangian? Okay, so I'm doing this because I'm working backwards. You know that what we actually do is once we write a Lagrangian and we plug it into the Lagrangian equation of motion, we get a force equation. Okay, this is what we have known. But now what I'll do is I know the force equation, which comes from where? From the Lagrange equation of motion, and from here I want to guess the correct Lagrangian. So I'm going in a reverse direction actually. Okay, we know that in the Lagrangian we have a kinetic term. Okay, so there is a kinetic energy term subtracted by it, the term which contains potential energy. Usually you might have seen in the books it is written T minus V. So this V is the potential energy we need to find. You will say why? Because you see, when a particle is moving, we know that kinetic energy of a non-relativistic particle is half m and its velocity square. But we don't know the corresponding potential V. Okay, so remember this V is velocity and this V is potential. Okay, to remove the confusion, I'll write V is a function of R. Okay, and we will see what else V depends upon. We will see towards the end. But now, okay, let's do one thing. Let me use U. That would be another good thing to do. So instead of V, let me use U. So this is the potential I'm interested, but I don't know what is the exact potential that I need to write to explain the behavior of a particle in electromagnetic field. So I'll do this. Okay, up to here we are done. What else we need to do? Now the idea is we know that everything in the Lagrangian is in terms of potential, so why not write this force of ours here in terms of the potentials? What kind of potentials am I talking about here? Well, we know that in electromagnetism we talked about potential phi. This phi is actually the electrostatic potential. Remember, we wrote electric field is equals to so let me write it completely. So let me remove this. So yeah, so electric field is equals to minus gradient of electrostatic potential, but I'm not going to use V because V we are using it for velocity, so I'm going to use phi. But we have done in our complete lecture series that we actually write it in this way. this is the correct way of writing electric field in terms of potentials. Okay, now the interesting thing is the A here is called as a vector potential, and it's also a function of R and T. So remember, we are doing everything in 3 dimension. Okay, now what we need to do, we need to write one more relation, how the magnetic field is related with vector potential. We know that magnetic field is related with vector potential as B is equals to del cross A. Okay, why am I doing this? I am doing all this because I want to write my force equation in terms of potentials, so that it will help me to guess what is this U going to be. Okay, so let's plug it in and let us look how the force looks. So F, which is the force experienced by the particle in electromagnetic field, turns out to look as, so in E, okay, let me put a vector sign here. Yeah, so in place of E I can replace minus of gradient of phi minus partial derivative of vector potential with respect to time. What else? There is a plus 1 by C, and there is V cross, now here we will write del cross A. Okay, del cross A. Now we all know what to do. So first let me remind you a relation. If you have A cross B cross C, so if you have this relation, then how to break it? So it becomes BAC. So I just remember it as Bach. BAC is like Bach minus CAB, cab. So it is my way of remembering this relation. CAB. So that's going to be A dot B. Okay, so let us now write how the force equation is gonna look. So it's gonna look as F equals, keep the Q here as it is, minus gradient of potential phi as it is, minus dA. Now remember, A is a function of R and T. Okay, remember that we are working in 3D, so don't forget that we are working in 3D. Okay, so this is done, and then we have 1 by C, and what the relation will get here, the first one we will get is del so yeah, del, so it's like BAC. So remember, this is our A, so A cross B cross C. Yeah, this is what we have. So we have BAC. So what is A? Which is V dot A. So this is what we have, and then there is a minus sign, and then we have C, which is A vector. C A, yeah, A vector dot V vector, and then CAB. So B is here. Okay, so this is what you get, but we know that the gradient operator will act on this scalar, because dot product of two vectors is going to be a scalar. So I can write it this in a different way. So what I'll do is I'll just write it in this way. What I wrote was correct, but for better way I'm going to write it in this way. So I'm going to write it as del acting on the dot product of v and a, which will give me a scalar. So gradient operator will work on this scalar. Okay, so we are reaching near. Let's continue further. So f. Okay, so let's put it in one place. So let me write it again. So minus, this is gradient of phi. Let me take a minus, come on. And yeah, this bracket here doesn't look good, so I'm gonna put another bracket. Okay, so take the minus common, and what do you get? You get dA divided by dt, and then you get a minus sign 1 by c gradient v dot a, and then there's a plus sign 1 by c del v dot a. Okay, till now I guess everything is correct, and let us put our bracket back. Okay, now there is a very interesting observation that we will see. We know that a is a function of r and t. Let us take a total derivative. So if I have a total derivative, okay, and I need to evaluate this total derivative, and to evaluate this total derivative I'm going to write it in this way. So d by dt, I know that my a is a function of, so in 3D you have x, y, z and t. Now why I'm writing in this way, it will become clear. So the first term is nothing but partial derivative of a with respect to time, okay, and then you are going to have del x divided by del t into del a, you can write it like this, divided by del x, and then continue with the other one. So you have del y divided by del t and dA divided by dy, and then the last term del z divided by del t dA divided by dz. Okay, and then this will become the following: dA divided by dt, and this entire thing can be written in this way, and you can verify that this is correct. V dot gradient acting on a, which is a function of r and t. So this is my total derivative of a vector. Okay, so let us see if I can find these terms here. Okay, so dA by dt partial derivative is here, added with v dot del acting on a. Okay, let's see if we have v dot del acting on a. I think we made a small mistake somewhere. Let's give a quick check here where I was. So here we have v dot del on a, which is here, and here we del v dot a. Okay, so we made a small mistake, so let's rectify it. This one, you see, I have written in repeat. Okay, so let me write the correct one. So it will be v dot del acting on a vector. Okay, I think this is correct. and also I need to rectify it here. So there is a minus sign and there is a plus sign, and this will become plus v dot del with a. Yeah, now it's correct. Okay, so we have just used this relation, and I just corrected what I made a mistake. And then what? Okay, so we have to find this term. Let us see if this term exists here. Yes, this term is here. Okay, now what? Now it's very simple. Now you will say what we will do with the c. Okay, you could have taken c common, or you can set c equals to 1. You can do a variety of things here, so I'm not gonna tell you what happened it there. So you can just put 1 by c here, no problem. You can just multiply 1 by c both sides and work out the entire detail. You can also do that. Okay, so anyway, the c will go inside, and what my final expression that I wanted is this. So this equals to q, now minus gradient of phi. This is what I got, minus in the bracket, oh let's yeah, now in the bracket I'm gonna have dA, total derivative of a with respect to time, and then minus, I can just, okay, so as I said that there will be c, let's do one thing. We can set c equals to 1. Okay, so let us not bother where the c goes. So let me set at this moment c equals 1. It would have been better if I would have worked with c equals to 1 from the very beginning, but yeah, so to not trouble myself here and also you, so I'm gonna set c equals to 1. So what I have, so I get dA by dt, and I'm gonna get minus del v dot a. Okay, I think the mathematics till now is quite clear here. Now what I'll do is I'll do just one more interesting step. I'm gonna just remove the bracket and the minus sign. Okay, so f equals q and then minus gradient of phi and minus dA divided by dt, and then there is plus gradient of v dot a. Okay, this is quite clear till now. And again let me tell you, okay, so let me write this here. Again let me tell you, if I take c not equals to 1, then I should have 1 by c here and 1 by c here, but just for convenience I took c as 1. Okay, and I have this. Now what does this expression look like if for a moment if you ignore this one, then don't you think that this Lorentz force F looks like minus of gradient of, so let's see how does it look, q phi minus q, this is gradient or acting on v dot a. And I know that there is a minus dA by dt term, I know that, but if I just ignore that for a moment just to build up my intuition, I see that my force can be written as a gradient of such kind of term, and this is a potential u that I can happily put in the Lagrangian. But remember, so now your question will be, if I put this u in the Lagrangian, then am I going to get exactly this force equation when I evaluate Lagrange equation of motion? Now your question will be, am I going to get this dA by dt term if I use this as a potential? my answer to you will be yes, you will get. Okay, and all you have to do is you need to evaluate it, and you will find out from where this dA by dt terms arises. Okay, so what was my final plan? My final plan was to write the Lagrangian. So the Lagrangian is, as I said before, my kinetic term is half mv square, and I was trying to find the u, and the above force equation tells me or allows me to guess what u can be. It is minus, so gradient of phi, and then minus gradient acting on v dot a. Okay, so let's break it. I mean, just remove the bracket, not break it. So you have half mv square, and I have a minus, oh, I forgot the q, so let me put the q here. So minus q gradient of phi, and then plus q, and what do I get? I get we don't need gradient, right? Why do we need gradient? We don't need gradient. Gradient occurs when I write the force equation. In Lagrangian, we can directly have the potential phi, and then plus q, I'll get v dot a. So all this in vector form. Okay, and since we are doing in 3D, so this is my Lagrangian in 3 dimension. You can break it in terms of components, so just for convenience, let me write it. So in terms of components, what you have to do is you have to write it as vx square, because v square was the vector, right? So you'll have vy square, and then you will have vz square minus q, now phi here as it is, and then plus q. Now there is a dot product, so there is vx ax, and then plus vy ay, and then plus q vz az. Why I did this is to make myself stand on an easy position to find the Lagrange equation of motion. Okay, for example, so just as an example, so consider you remove all the other components apart from x. So if you set this as 0, and just for our convenience, you can also set happily these things to be 0, then what you will get? Then you'll get a simple Lagrangian that looks like half m vx square, and then there will be q of phi, but this phi will be a function of only x now, and then you will get q of vx ax. Now why I did this? To give you an example how to do the Lagrange equation of motion. Now, all you need to do is now evaluate this thing. So dl by del vx minus del L by del x equals to 0. Okay, now evaluate this and see if you get the force equation all in x component. So my guess will be, if you solve this, so let us look at our force equation again. Yeah, this is our force equation, and everything will be in terms of x. So you should get force equals q, and since I removed other components, so this becomes a 1D problem. Okay, so it's gonna look like minus d phi divided by dx. You should get this term, and dax divided by dt, you will get this term, and then most probably you will get d by dx of vx ax. Okay, just give a quick check whether you're getting this equation or not. Similarly, if you can do this in 1D, you can also do it in 3D. Okay, easy. Now the story doesn't end here, but unfortunately I have to end it here. But I'll give you a quick idea what the Hamiltonian is going to look like, because once we know the Hamiltonian, we can write the Schrodinger equation of a non-relativistic particle in an electromagnetic field. So the Hamiltonian is going to look like this. You will have P, so I'm write it in 3D, P minus QA square divided by 2m. Remember, I set C as 1. Okay, so this is one part, and then you'll get plus Q phi. This is your Hamiltonian. Now question is, what is P? Now P is actually, for example, all the components of P can be evaluated as the following. So let me not write the P vector. Let me tell you how you can evaluate the P. Now P is actually conjugate momentum, and you can calculate this in this way: del L by del VI. Okay, for example, if you want to calculate the X component of conjugate momentum, then you have to do this. Now there is a very interesting thing I'm gonna say. So when you're doing classical mechanics, you will deal with two kinds of momentum, and many people get confused with these things. So you have one momentum which is the actual momentum. So why I'm writing the actual momentum, I want you to remember your momentum, which is nothing but mass into velocity. This is the momentum that you have studied. But here we are talking about a new momentum, and it has a new name. It's called as conjugate momentum. And remember, conjugate momentum is not equal to the momentum mv. So there is a physical meaning behind conjugate momentum, which I will do it in maybe in the next video. But conjugate momentum, which is P here. And you know how conjugate momentum and this is related. You will find that pi plus QA is actually the conjugate momentum. You can find it from the Lagrangian. Okay, let's take the 1D Lagrangian. Where is our 1D Lagrangian? Here. And let's calculate px. So just for computation, I'm gonna do this calculation, just one calculation. So if you do del L by del Vx, okay, what do you get? You'll get mvx. The second term is independent of velocity, and this one you'll get q ax. You see? Okay. So now you can use this Hamiltonian, plug it into the Schrodinger equation, and then you will have a Schrodinger equation of a non-relativistic particle in an electromagnetic field. Okay, so I hope after this long lecture this idea is clear. So when you do not have any idea exactly how to write the Lagrangian of a particular system, you can actually work backwards. This was my plan to teach you that you can actually work backwards and find or guess the Lagrangian, and then you can check whether the Lagrangian is correct or not by doing what? By finding the Lagrangian of motion. Okay, so again